welcome to Boyle here. So, as you know, we all work for STFC. STFC is runs the labs, but also funds science, and part of the science it runs is in particle physics. And we have, so as part of COSEC, I went up to Edinburgh to talk with the theoretical particle physicists up there, and they were all very clear that the thing that made theoretical particle physics works is sparse matrices, and in particular, were very, very complimentary of Peter's code grid, which is the underlying workhorse that does lots of modern particle physics. So yeah, we went up there. I came back down, talked to Sam and many others in here. This guy, Peter Boyle, it's a shame he's no longer at Edinburgh, but we really need to come in to visit or give us a talk or something. And then we saw that he was in the UK, giving a talk and a workshop, and said to Sam, let's invite him over. So it is a great pleasure. So Peter is, I guess he did maths and physics as an undergraduate.
Maths and physics undergraduate, yeah.
And then did a PhD in theoretical particle physics. Was working at the University of Edinburgh for many years. Then got poached to the other side of the pond, and in 2019, I think he said you became a staff scientist at Brookhaven National Labs. Expert in theoretical particle physics, expert in high-end HPC, high performance computing, and in particular is on that intersection between maths that we all know and love, and getting to work in particle physics to make particle physics calculations. So I'm very much looking forward to your talk. Over to you, Peter.
Thank you. The focus of this talk was predominantly on the algorithms side. I think it's probably more interesting to the group here, but obviously the grid, the software, I'll just mention is just cross-platform portable. It runs CPUs, vectorized various forms of, using boiling down at the bottom to inline intrinsics for Intel vector instructions, AMD vector instructions, ARM, Neon vector instructions, and SVE and stuff like that, but also runs across AMD, Intel, and NVIDIA GPUs as well. And I'm not really going to talk very much about that aspect of it, but feel free to talk to me later or something like that. I've got whole other talks in that kind of direction, but this talk specifically is about the intersection or algorithms that we developed under the SIDAC project, which I'm the PI for in the US for USQCD, which is and somewhat like the COSEC direction, there are these SIDAC institutes, Fast Math, Rapids, where applied math areas of the DOE collaborate or work collaboratively with domain scientists in high energy and other forms of physics, plasma physics, you name it. Here our collaborations directly with the PETC team in FastMath, who I believe some of you will know, specifically Matt Nepley, who is an absolute star, and I have the pleasure of talking to at least weekly, and sometimes more often than that. Okay, so the overview, I'm going to talk about solver algorithms in general. I love solvers, multigrid algorithms, then multigrid preconditioned blocks EG, and then talk about the performance of the algorithm when applied to my specific matrix. And the multigrid algorithms. So we're dealing with a gauge theory. Phase is locally defined in a gauge theory, with the result that local averaging makes no sense, right? If you change gauge, A plus B becomes A minus B with the appropriate phase transformation because we have a local gauge invariance to the theory, and we do not fix the gauge in our calculations, with the result that unlike conventional multigrid for classical field equations, we do not know how to define a blocking transformation to smooth the variables, because smooth in one gauge is non-smooth in another gauge, right? Okay, so, and therefore I'll come to the formulation of multigrid algorithms, or specifically multigrid algorithms for gauge theories, are rather more complicated and are actually end up being semi-algebraic in the methods we use. I'll principally discuss a paper I put out now almost 2 years ago. This was a multiple right-hand side multigrid for domain wall fermions. It uses GPU matrix hardware efficiently, these tensor cores that everyone, they're apparently transforming the world these days, and going to make everyone redundant eventually, apparently, allegedly. Multigrid, preconditioned block CG, and in the end, in the test system, we gave a over 20x speed up by improving the effective condition number of the preconditioned system. This is our SIDAC project. We have MIT, LBNL under PETSI, City Buffalo under PETSI with Mark Nepley. The people in black are the investigators, the people in red are the people who are employed on the project directly, and large number of labs and universities in the high energy theory side, covering both the RBC collaboration and the Fermilab Milk collaboration in the US. Okay, so motivation and introduction. Well, first I'm going to start out with Markov chain Monte Carlo. What are we doing? We're doing the Feynman path integral for QCD. We do that by Markov chain Monte Carlo integration. Markov chains generate a sequence of states where you have a transition probably from state X to X prime, where the rule depends only on X. This is usually composed of a proposal probability, how likely you choose X prime given X as a probability distribution, and then an acceptance probability of do you then take the step or not, having proposed X prime. You design the rule to yield the desired equilibrium probability distribution after many transitions, and a necessary condition is that the equilibrium distribution should be a fixed point of this transformation, and then you might have a chance of converging on this target distribution that you're looking for. And an ergodic update satisfying this and being a contraction map, it will become a stable fixed point, and you'll converge in this distribution. This is a high-level sketch. You then introduce a detailed balance probability. If you satisfy this condition, then sum over X, you then see that this is indeed a fixed point of the Markov process, and you can use this. And then when combined with you're designing a target, a distribution where given any proposal probability distribution that is ergodic and an acceptance probability where if you know your target designer distribution and you satisfy this condition as your accepted X step, you then converge in the target P equilibrium distribution that you put in as the fixed point, right? So this was invented essentially in the DOE nuclear weapons program, simulating neutron populations and things by Rosenbluth, Teller, and Metropolis, where allegedly, according to Wikipedia and so on, Metropolis was really on the computing side, and the algorithms were proposed by Rosenbluth and Teller, and their spouses, Rosenbluth and Teller, did the implementation. This is in the days before compilers, this even before assemblers, right? They're writing machine code, did the first ever MCMC simulations, and I think are worth mentioning because Ariana Rosenbluth and Augusta Teller wrote the first ever MCMC simulations in machine code by hand on early computers, and somewhat as a travesty, this is now called the Metropolis Hastings algorithm, right? So it's worth remembering that two excellent, Rosenbluth and Teller, their husbands were famous in their own rights. Teller particularly famous, I guess, but history is sort of forgetting some very leading early applied math, computational mathematics contributions by female mathematicians in the US national lab systems. And that's why I don't like the words Metropolis Hastings describing this algorithm. It should be an MTTRR algorithm, if you want. Okay, so with that said, we're now using this Monte Carlo, which is embedded in lattice QCD. It's used across statistics and even machine learning. I'm going to particularly call out Brian Pendleton and Tony Kennedy. Brian was my PhD supervisor. This maybe give me a somewhat biased and vested interest in saying that. So hybrid Monte Carlo, we perform an additional Gaussian integral over a conjugate momentum field whose purpose solely is used to evolve in a correlated fashion the state space that you're integrating over. So you pick a random direction. I kind of sometimes describe this as Lineman's crazy golf, where you pick a random direction, you hit it, you let it run, following whatever trajectory it has, conserving probability within this joint probability distribution for the Gaussian plus the state space you're integrating over, where the weight function for the state space is given by this eta minus SG, where G is the gluon action in our case. And you do this repeatedly applying a metropolis accept reject step. And by preserving this constant joint probability, you end up with a very efficient sampler that both moves the state in a correlated fashion, but very rarely gives up probability. So, yeah, and the key point here is that the fermion action is implemented. So we have a determinant, the Pauli asymmetry is implemented as the manifests itself as the determinant of this Dirac operator matrix. That total anti-symmetrization is implementing the Pauli exclusion principle effectively. The determinant we can encode as a Gaussian integral because we know how to do a Gaussian integration. You get the 2 pi sigma for a Gaussian integral, eigenvalue by eigenvalue over this matrix. You can, if it's a Hermitian matrix, you can diagonalize it, then it's just a product of in this diagonalized basis, the product of Gaussian integrals, and you get the product of the eigenvalues coming out because of the root 2 pi sigma. And it's squared, so the eigenvalues, the fact that eigenvalues, the fact that this is a complex integration, so you get two factors that give you the squaring gives you the determinant of this matrix. This a stochastically implemented determinant. And the key point is, as we establish our Hamiltonian mechanics in the microdynamic space for this inverse that's required to give the determinant, because the 1/2 sigma squared in a Gaussian integral turning into root 2 pi sigma in the upstairs, that means you have to have the inverse here, which means that the microdynamic force equations that we form in this will involve matrix inverses at every time step of our microdynamics integration into a hybrid Monte Carlo. Right? So, and the key point also is that this matrix is a function of the gluon fields, the gauge fields, and its coefficients are changing and are semi-random. It's the gauge theory with the randomly being sampled gauge degrees of freedom, with the result the phase is rotating everywhere, and the matrix is changing in a way where, for example, setup cost for establishing multigrid becomes quite expensive and has to be repaid every time you take a time step. Okay, so I'll just make the final point, which is we're integrating over a group manifold. So these are SU3 gauge links that we're using. The gauge degrees of freedom live in the SU3 manifold. And you can think about how we're doing this. We're picking random directions to shoot in the tangent space. And that you can think of that being, we can integrate over the surface of the Earth, SO3 being, if you substitute the group for SO3 for rotations, if you just live on the surface of the Earth and pick a random direction and keep repeating walking in random directions, eventually you will map over with equal measure every point in the surface of the Earth, which is how we're doing the group integral in this case. Yep.
What is MDAGA?
MDAGA is the adjoint, so transpose complex conjugates. So we're always dealing with complex matrices. So we always take, in applied math, people normally say symmetric, and I'll always say Hermitian, and just take Hermitian to be symmetric for the sake of argument. Right? You could always write things as a real and imaginary pair of degrees of freedom anyway, right? In which case,
how big is M?
10 to the 10, typically 10 to the 10 by 10 to the 10. So it's a sparse matrix, right? But the vector field it's operating on is roughly 10 to the 10 degrees of freedom. So our current state-of-the-art simulation is 120 cubed by 288 by 16, with then 12 degrees of freedom on every side of that grid. So yeah. So the probability weight, we represent the action of QCD. So in other words, how you define a given field configuration, how you associate an energy with that, right? If you think, simple Stokes theorem. So if you ignore non-abelian gauge theory and just think about the abelian case, and you have a small loop, right? Then that is. The Stokes theorem would give you that the line integral of the A mu around the field is the integral of the curl related to the integral of the curl over the surface connecting it, right? And that curl you would relate to the field strength tensor F mu nu, right? the kernel being new. So basically, we deal with these linked degrees of freedom as the fundamental degrees of freedom, but we build the action as being determined by the product of links around a loop, which you would relate by Stokes' theorem to the kernel through the perpendicular area, which we then use to basically define the gauge action in terms of the sum of the plaquettes over what we call these fundamental loop variables, the plaquettes, and the sum of the plaquettes over all the lattice give us the energy of that whole gauge configuration. Fermion discretization is done. The naive way would be to have a finite difference equation where you have these Dirac matrices. This was a first order. It's a first order derivative, first order differential equation, the Dirac equation with these Dirac matrices. This has the famous doubling problem where discretizing a first order derivative of a symmetric Bagler form is finite difference gives you the sign p mu, which will give you 0 at the origin in the Brillouin zone, but also 0 at each of the corners of the Brillouin zone if any component is pi, right? With the result where you have this spurious poles in the propagator, which would be unphysical but appearing. And Wilson famously solved this by introducing a Laplacian regulating term, which we call the Wilson term, which gives you only the pole at 0 lifted by these extra terms at the boundaries. This breaks chiral symmetry famously, and leads also, and as a consequence, leads to an unphysical non-particular additive master normalization, and has all sorts of and it necessarily introduces order A relative errors to the discretization. This was fixed with what are called overlap fermions, where with a non-local operation, so if you take an inverse square root of this Wilson matrix in some form, and that's a non-local operation, you end up preserving chiral symmetry and having an order A term only at 0 distance and not away from 0 distance, so it's theoretically beautiful, but gives up locality and replaces that with the exponential locality in what we define to be the matrix. And this ends up being in practice handled with a very clever trick in the fifth fictitious dimension in what we call the main wall fermions. Why are we doing this? Well, I like to give the example of hadronic vacuum polarization, which is highly competitive, where in the field of lattice, where these contributions to mu on G-2 are the dominant theoretical error and are required. The Fermilab experiment has just finished its final run and announced that they have achieved their target precision, which is something like 4 times smaller than the current theoretical error. And somewhat famously, the prior theoretical error was based on basically using E plus E minus to real pions to infer contribution of E plus E minus to virtual pions using what's called the optical theorem. That process of looking at experiment to say what the standard model predicts, people should spell a rat. Looking at the experiment to say what theory predicts is not a theoretical prediction. It's using one experiment to predict another experiment, whether or not that first experiment was actually the standard model, right? And that approach was a phenomenological approach that was always gave a better error than lattice results over the years until very recently. And very recently now, lattice results have become equally precise and discrepant from the prior phenomenological approach, and ended up being in agreement with the Fermilab experiment, reducing what was a 4 sigma tension to nothing. But at the same time, new E plus E minus experiments, there's something called CMD3 in Novus years, has come in and said, actually, we agree with the lattice result and not with the prior experiment. So effectively what's happened is the process of peaking its experiment to infer theory has been subject to underestimated prior experimental errors, or whether it's the new ones or the old ones, the spread they would infer now covers the Fermilab experiment and the lattice results, and the errors from that approach necessarily should go up. And they've simply said we can no longer make a meaningful prediction. And at the same time, lattice calculations become the dominant or gold standard way to decide whether or not this tension is a real tension. And we now find that actually lattice, and this is our calculation, but BMW 2020 was the first to be indicating favouring the Fermilab muon G-2 being correct rather than discrepant, and the prior phenomenological results are have problems because of the bigger spread in experiments that have arisen in the last few years. Okay, so next steps for us, in order to prove our calculation, we need to reduce our finite volume error. When the 96 cube by 192, we're also simultaneously running now 128 cube by 288 calculations on the Aurora system. Right, the second step is double the physical box in every dimension. That's 16 times bigger than a 4D calculation. Our algorithm has a volume squared element. That's 256 times more storage, memory, etc. We're currently storing petabytes of eigenvectors to deflate our solves in our analysis. Storing 256 petabytes or more is bigger than the physical disk system of all the US supercomputers presently. So therefore, we've hit an algorithmic wall, and we need to eliminate the volume square component of eigenvector deflation to do our calculations. So we need to schedule innovation to solve the problem. So solving this equation, as I said, is central. We both use it in the evolution to do the Markov chain Monte Carlo, but we also use it in the data mining or correlation function calculation portion of the calculations. So what do we do to solve the Dirac equation in the free field or perturbatively? Well, we make a unitary transformation to a basis in which the action is diagonal, right? That's the plane wave basis. We know that from the beginning because the action was translationally invariant. We invert that diagonal matrix. We take 1 over the eigenvalues and reverse the transformation again, right? And that the Fourier methods where you know that's just going to the plane wave basis. In a Hermitian system, so if we square it, it's Hermitian, it's diagonalizable. We make a unitary transformation to a basis in which it's diagonal, take 1 over the eigenvalues, and we reverse the transformation. And this gives us the inverse, right? So, and the nice thing is that if you take a polynomial of d dagger d of this form, that's just a polynomial acting nature of the eigenvalue. So you can make if you could make a polynomial approximation eigenvalue by it that's accurate over the range of the spectrum, such that the polynomial of each of the eigenvalues is equal to some precision 1 over the eigenvalue, you have inverted the matrix, right? Or you have a routine, a polynomial of a set of polynomial coefficients of the matrix that you can apply to any vector and get the inverse of the matrix acting on the vector to whatever accuracy the polynomial reproduces.
Can you remind me
1 over the eigenvalues.
What sort of dimension is V?
Sorry?
What sort of dimension is V?
So 10 to the, roughly it's 10 to the 10 squared.
10 to the 10 again, is it?
Okay.
So you're not storing V?
So we're not storing Z. So we typically, we're not storing V. So you instead write a routine. It's you write a routine that applies D inverse, right? So, and with order, the polynomials, if we just run CG without deflating it, it's something like 26,000 iterations or so. So, minus 10 to the 10 matrix 26,000 times. And then you have one of the inverse. We do 10,000 of these inverses per gauge configuration. We do hundreds of gauge configurations. And we burn 20% of some of the biggest computers in the world. I got an email a couple of years ago from an Intel guy who was running in the burn-in of Aurora in Argonne. And the email contained no content, but the title was Grid at 30 megawatts. Okay, so Krylov-Sparse solvers. So so we sample the Boole field, right? We have to invert these. We build a Krylov space in some way, and we have some algorithm for choosing the Fourier coefficients. This is simply to emphasize that essentially, if you want that for CG, if you minimize the error in the A norm, you can very, very simply then say that given a search direction, you could create A orthogonal search directions. And then if you take the component of the error, the residual with respect to the row J, that lets you read off the coefficients that you want for each power of the matrix as you go through this Krylov space. So this is easy as picking off Fourier coefficients, except that rather than being orthogonal Fourier modes, these are orthogonal search directions, and you work out the component of the solution vector of B with respect to each of the search directions rho, and that gives you the alpha that you have to pick out for each term in the Krylov space. So that's how conjugate gradients works and was introduced. We use CGNR because we have this non-Hermitian matrix, but we square it and then solve the NR equation, and we actually red-black precondition it in the usual case. So what we squaring it is suboptimal because we, in principle, well, in some sense, physicists sometimes use sloppy, almost semi-empirical approaches to maths, which kind of annoys me. A mathematician would be getting really annoyed by this, right? They say, oh well, if we square the system, we square the condition number, and they're pretending that the spectrum of the non-Hermitian matrix is in some way directly related to the spectrum of the Hermitian matrix. It's like the pseudo-spectrum or whatever. But clearly, it is possible that a non-Hermitian algorithm, not squaring it, could be better, but for it's depending on the nature of the system, the spectrum of the square of it has spectrum of the singular value decomposition. The spectrum of the matrix, rather than it's right, into the right eigenbasis, is not necessarily clearly related, but it would be good if we had a non-Hermitian algorithm. As I said, Nick Bethan had this wonderful paper where, looking at non-Hermitian algorithms, there are cases where each of them takes of order n the matrix dimension to converge. So you could always construct non-Hermitian Krylov solvers a pathological case. And in our case, our spectrum looks something like this, and in the infinite volume limit, the spectrum is dense. The origin is here and is enclosed within the spectrum. And the argument I would make here as to why we would obviously suffer trying to invert this matrix is that there is in principle a locus. If we take this is something like 16 cubed, if we take 128 cubed, there's a locus living entirely in the plane of the spectrum, over which, if you integrate 1 over z that you're trying to approximate, you get 2 pi I, whereas if you're integrating any polynomial of z, you get 0, right? So a stock Krylov will necessarily fail, or in other words, will necessarily have to disagree with 1 over z in the gaps between eigenvalues, which are becoming increasingly dense as you take a bigger and bigger volume, right? So the need to have something that's wildly oscillatory and a polynomial of order the system size is going to arise for us. Deflation, well, we know there's the Chebyshev convergence bound that this is going back to SAD or whatever, where SAD's book where it's well treated, where the worst case convergence rate is square root kappa minus 1 over square root kappa plus 1, where kappa is the ratio of the largest smallest eigenvalue. And if you deflation, the idea is if you calculate with some iterative method of Anschauss the lowest n eigenvectors, you can lift the condition number, you can reduce the condition number by removing these eigenvectors from the problem. You know that eigenvalues take 1 over that, and then on the orthogonal subspace, you run the solver and deflate, and that gives you a faster convergence rate. This is our convergence history from CG. What's actually kind of interesting here is that we compare 96 cubed by 192 to 48 cubed by 96. And the convergence history in 2 different gauge configurations is actually almost identical to each other. And this is, of course, saying that the convergence rate is a function of the spectrum, right, and not the detailed positions of individual eigenvectors, or in some other sense, we're in the highly dense, like it's of order 10 to the 10 eigenvalues. We're using an order 26,000 polynomial to converge this. Obviously, each wiggle of the polynomial is getting many, many eigenvalues covered in it, and we're hitting the worst case bounds where the spectrum is very, very dense compared to the ripples in the polynomial that we're using to approximate the inverse. So with the result that we're basically saturating the worst case bounds. And if I measure the convergence rate in this tail, I get this, the convergence rate is 0.999451. If I calculate the lowest and highest eigenvalue in the system, it says the convergence rate should be 0.999445. Right, so this is like 6-digit agreement between the worst case and what we actually get out of CG. Okay, so we're in a large volume limit, etc. Okay, actually, so multigrid algorithms. So the way lattice works, this is a schematic. As I said, phase is locally defined in a gauge theory, and you can apply a gauge transform, and every single site's fermion field will rotate by an arbitrary complex number. Arbitrary complex root of the identity is e to the I theta. Then the idea then, therefore, is that in a semi-algebraic way, we learn the near null space of the Dirac matrix, right? Something like 60 vectors, 30 vectors, 40 vectors, 80 vectors. So how do you learn them? Well, you don't know anything about them to start with. So you make up a random vector, and then you apply a polynomial of the matrix in some way that breeds out the lowest lying eigenvalues and suppresses the higher eigenvalues. So you can use inverse iteration where you apply a solver to it to enhance the low modes by a factor of 1 over lambda. You do that n times and you enhance them 1 over lambda to the n, and you're left with only low modes. Or in my case, I say, well, we've got a Hermitian matrix, real spectrum. Uncle Chebyshev tells you some really good polynomials to use, and I'll use those ones, right? But however you do it, you apply some filtering scheme where you use the Dirac matrix itself to covariantly read out of noise vectors that are rich in the low modes of the system. And these are a little bit like then algebraic vectors that you're going to, algebraic degrees of freedom that you're going to use, except we introduce the idea of local coherence, or what I call here a local wavelet basis, where you take these vectors you produce and you say, well, maybe many of these low modes are locally similar to each other, but globally phase rotate or whatever. And we just break them into little wavelet chunks with some compact cuboidal domain and say each of these will become a coarse degree of freedom. The inner product with this chunked vector will become a coarse degree of freedom. And by breeding 60 vectors, divide them into, say, 10 to the 4th chunks, we have 60 times 10 to the 4th coarse degrees of freedom rather than 60. Right? So we're making economical use of the projection into this coarse basis. And then the idea being, schematically, well, if you take the first or second derivative operator, the constant mode is the lowest mode of that operator, right? The next mode of the violin string will look somewhat oscillatory. It'll be, a sinusoid. But if you re-expand that next mode in terms of local segments from the constant operator, the constant mode, you kind of get something that sort of reasonably approximates it over the full range, right? You might then want to go and smooth off those edges a little bit, take a file or whatever, and that could be a multigrid smoother that you apply. And then you would actually do rather better in re-expressing the n equals 1 mode in terms of the n equals 0 mode, right? And this being done in a way where we're dealing with 4-dimensional cuboidal blocks and all of the phase ambiguity of the gauge theory being absorbed is essentially what we're doing. And we're typically picking things like 4 to the 4th subblocks of these near null vectors and something like a basis of 60 modes living in there. And if you remember this 4 to the 4th, there's also 12 spin color degrees of freedom in there. So there's 12 times 4 to the 4th degrees of freedom, which we then, in defined space, which then compress into these 60 component amplitudes when we define the coarse degrees of freedom out of these. So that gives us some compression basis. So we have these low mode vectors, we generate phi k, we take the phi k's and restrict them into local blocks, B, and then we work out, and we have a projector which goes from the fine space into the core space, into the subspace that spanned by these, right? And we project the matrix into the coarse space to the core space and find their complement and so on. So we basically can project the matrix, and then taking the inner product of our matrix M with respect to these gives us the coefficient matrices of a coarse operator that within the subspace S to S, it faithfully replicates the fine matrix because we've defined it to have the same matrix elements in that subspace to that subspace as the fine matrix had. And in as much as these then capture the low mode degrees of freedom, you represent the coarse matrix will represent the low degrees, the low frequency degrees of freedom in the fine space at the end. And having defined this matrix A, you can invert it on that subspace, right, and use Krylov methods to get the inverse of the coarse operator.
You say multigrid, how many levels of multigrid?
So this is argued. It's like, you know, there's this like the true Scotsman mythology. Oh yeah, not a true Scotsman, right? It's not a true multigrid. Apparently, it's not a true multigrid unless it has more than 2 levels. But then if I eigenvector deflate the second level, that's a 1 to the 4th coarser grid. Is that a true multigrid? Or, you know, so our colleague Richard Brower in Boston will talk about what's a true multigrid and what's not a true multigrid. And of course, that's judiciously designed to make sure that what Lucier did before him wasn't a true multigrid, whereas what Richard Brower does is a true multigrid and not a 2-level multigrid. So, you know, you tell me, is multi more than 1 and if more than 2, and if or is multi, does 2 count as multi, and does 2 plus a deflation step, which is 1 to the 4th.
Just if you're going
it's 1 to the 4th a grid. I don't know.
you're going from 10 to the 10, and the next level is 10 to the 8. That's still huge. You'd rather keep going down.
More a 4 to the 4th, so 60. So it's 200 times smaller. Yeah, so 10 to the 8, 10 to the 7-ish. Yeah.
So you'd hope to do probably 4 or 5 levels.
Yeah, and what Brower will then say is that Lucier correctly made a mistake in that his approach was not tolerant to imprecise solution of the coarse grid. He had to solve it to the final convergence accuracy, and that was a mistake, and that was a bigger mistake than not really supporting recursion in the multigrid, in my view.
But then you're down to 10 to the 4, 10 to the 5 unknowns, and we can all do that.
Yeah. Okay, so so for many years, Wilson Clover twisted mass has had a successful multigrid that sets up and runs so fastly that they've effectively dropped deflation, has order of magnitude gains. For my formulation domain wall, which has this much more difficult spectrum, there hasn't been a multigrid supremacy and staggered fermions as well. I came close with HDCG in 2014, where with the coarse operator, because we squared the operator, this nearest neighbor operator actually becomes an 81-point stencil in the core space. It's kind of expensive, but I did get an order of magnitude gain in 2014, where a multigrid cycle was introduced to a preconditioned CG as a flexible preconditioned CG, specifically one called ADEF2, that floats around as a CG preconditioner. And I used as a smoother, I used a low number of iterations of CG, but this didn't float around in the field. So there was Diane O'Leary, you guys seem to know the people better than me. So did something called, I think it was yet another polynomial preconditioner where she used CG as a preconditioner for CG. And the problem with CG is that it works for symmetric positive definite matrices. If the matrix you're using is not positive definite, even if it's symmetric, it will fail to converge. And using a recorded CG polynomial as a preconditioner for CG, the problem is that the polynomial CG produces at low iteration counts can actually be indefinite and cross zero, even though the matrix itself does not, right? And she said, well, this is easily detected, and you can, if it doesn't converge, you use a higher order or something like that. I introduced add a constant to the matrix and make that a tunable parameter, because you can hide the low modes of the lower range of the matrix from the CG's coefficient selection. For CG, put blinkers in CG, and they look only at the high eigenvalue region where H is much bigger than lambda. And that regulates her proposal of CG as a preconditioner for CG. And this makes for a really good CG smoother as a result, because I can control the size of the ripples and tell it where in the spectrum of H do I want it to look at.
Of course, the big question there is, what is this perturbation you're making? So what is this perturbation? Do you know? Do you have some bound for this perturbation you're going to have to elaborate?
So, for example, if you want 7, if depending on the order of the CG, that sort of dictates how. If you know the lambda max of this, and you can with order 10 iteration polynomial, you can keep the polynomial fairly well bounded and not crossing a 0 if you go down to an order of magnitude below the maximum eigenvalue of the matrix. And however deep you want to go below the maximum eigenvalue by ratio, that kind of dictates the order of the polynomial you can get away with.
But by doing that, you're perturbing the system. So you're getting CG converting faster to the wrong problem. Is that right?
Well, eigenvalue by eigenvalue. I mean, at the highest eigenvalue, it's kind of if this number is order. So I think this number of order 1. The range of the spectrum is roughly 90. Right, so it's kind of 1% effect at the high end of the spectrum, and 100% effect, obviously, eigenvalues of 1. Right, so for a smoother, where you're trying to target the high eigenvalues, it's okay in percent scale. Okay, so and then ADEF2, basically you take a smoother and a coarse grid correction. So you effectively say that xi plus 1 is the coarse grid correction, and then you apply a smoother, xi plus 1 is a smoother acting on the current residual, and then xi plus 2 is the coarse grid correction applied to what you had for xi plus 1, recalculating the residual, and combine that together, and you're just algebraically rearrange it, and then you end up with this as being your net preconditioner. The MIRS is the smoother I introduced, and the Q is the coarse grid correction. So the first step was I re-implemented HDCG in grids to run on more than GPUs. The coarse grid was expensive and difficult to optimize in GPUs, as there's not enough work compared to the fine grid. It's latency dominated, etc. And I rapidly concluded I needed a multiple right-hand side implementation to make it more flop rich. So why do you go more flop rich? Yep. So if you're applying the same matrix to multiple right-hand side, you can save on loading all of these coefficients. Basically, you promote from being matrix times vector to matrix times matrix operations. So, yeah, when the number of right-hand sides is much less than this number of basis squared coefficients for loading, essentially you can apply to multiple right-hand sides in the core space for the same cost as applying to one right-hand side in the core space. Also, you can get faster algorithms. The block algorithms are known to give better than or superlinear convergence in certain cases. So there's some hope, and I don't know where this is written up prior to me. I mean, it's obvious, right? And sometimes there's block CG and traditional CG put them together, and you have a preconditioned block CG. The problem only is that in a multigrid, you really would want a flexible algorithm, because you have a Krylov smoother or something like that, and making the block CG become flexible preconditioned block CG would involve a huge amount of linear algebra, because you're orthogonalizing n search directions with respect to n squared times the history from the orthogonalization in a flexible algorithm. So I also, at this point, started replace a CG-based smoother with a fixed order Chebyshev polynomial-based smoother, in order to make a static preconditioner rather than a variable preconditioner. So, and as I say, that going from the derivation of preconditioned CG from CG and applying that to the block CG, you just have to change the inner product in which you're operating as you derive the algorithm. So it's kind of semi-obvious, right? I made the preconditioner stationary by using a Chebyshev polynomial over the perpendicular. Oh, sorry, I find this updates. I calculate n eigenvectors with Lanchos. I deflate those, so you have the 1 over the eigenvalues applied to this, and then on the orthogonal subspace, I apply a Chebyshev polynomial rather than a Krylov on the orthogonal subspace, and that keeps the preconditioner static, which means that you don't have to worry about having a flexible algorithm, which has the effect then of making block CG cheap, or relatively cheap. Okay, so I define the course operator. So I use Chebyshev polynomials. Chebyshev polynomials, we know, wiggle univariate between 1 minus 1. And when you scale the matrix coming in, you can arrange, therefore, that outside the range where the thing wiggles, rises like high power. Use T500 that goes like delta lambda to the 500 coming away from the edge of the spectrum. So you can create something which gives us a very rapid enhancement of the low mode region with judiciously chosen Chebyshevs. And having done one first pass enhancement of the low mode region, I can apply other Chebyshevs that have sign crossings across that region to breed out linearly independent vectors that still live in this low mode rich environment coming from this. Okay, so we have various ways to define our course. We can either use exact eigenvectors or these filtered eigenvectors. I can compute on the fine matrix the say 200 eigenvectors or 200 most eigenvectors of the fine matrix, and with the different bases, I can project into the coarse space, promote back up to the fine space each of these 200 eigenvectors, and ask how complete, how close is that to the identity when acting on a low-lying eigenvector, and calculate the defects. And you can see that we're 99% or so complete. The eigenvector, lowest lying eigenvectors, lowest lying 200 eigenvectors, when represented in our coarse degrees of freedom, we put back to fine, and subtracting off the original, we're within 1% accuracy of faithfully describing these degrees of freedom in our coarsening. When I use the first 60 eigenvectors as the definition of our coarsening, chop these into blocks, and then project, this is displaying what we call local coherence, and project 200 eigenvectors into that coarse basis and promote back to fine again. Of course, the first 60 eigenvectors I use as input, they are faithfully and exactly up to numerical precision represented by the coarse basis, and the ones thereafter are at the percent scale faithfully restored, right? So you see this property of local coherence where chopping low modes into blocks and representing other low modes is working at the percent scale accuracy, right? So this, we call this local coherence. I think Bresina and so on call it the weak approximation property. But the idea is that locally low modes are similar in physical systems, but globally they differ from each other, and you can use the local segments to represent many more of them than you originally start with, to some level of approximation. If I look at the spectrum of the coarse matrix and compare that to the spectrum of the fine matrix, the spectrum of fine matrix is very low eigenvalues. So that previously looking at the fidelity of the eigenvectors, this is the eigenvalues you have. If I input exact eigenvectors, the lowest, if I input 60 low eigenvectors of the fine matrix as the definition of my coarsening, chop these into blocks, the first 60 low eigenvectors of the coarse matrix are exactly the same as the low eigenvalues of the fine matrix. And then beyond that 60 that are guaranteed to be exactly included in the subspace, the eigenvalues jump, right, by 2 orders of magnitude. The coarse operator with respect to the fine operator. So you see that we're pretty well approximating the eigenvectors, the eigenvalues lifted when they are not those vectors exactly containing the basis, right? So the spectrum, graphically, if we input 60 vectors, we get 60 beautiful eigenvalues, and then we get lifted eigenvalues above that with some density, right? That means that that mismatch of the eigenvalue was about 2 orders of magnitude here. We're sort of okay in a multigrid to converge by 2 orders of magnitude, but then have to go back to the fine grid, recompute the residual, and go again, right? Which is why we're ending up in a very classic multigrid algorithm, where you compute in the coarse grid for a bit, promote back up, smooth, recalculate the residual, and go again. You reduce the residual. You can reduce the residual in the fine system by 2 orders of magnitude, but by no more, because at that point the coarse grid correction is just wrong at that level of approximation. And this is showing the 48 and 96 tubes. The low-lying, 60 low-lying guys are present both. The density of modes above that has gone up by a factor of 16. So 3 modes per bin to 48 modes per bin, right? That factor of 16 is just the volume factor because it's 16 times bigger. For this system, the spectral density has to be 16 times bigger, right? So we understand now in detail the spectrum of the coarse matrix. In terms of performance, on this test system, we got a straight factor of 20 wall clock gain in the convergence. This is on AMD computers like LumiG and Frontier. Yep, and the convergence in terms of fine matrix multiplies has moved from this situation to this situation, and it scales with volume. So we compare to deflation with eigenvectors, which is formally a volume squared algorithm. Each eigenvector is of size, volume, and the number you have to compute to deflate by the same amount grows by the volume. So it's volume squared, right? This has now become an order volume algorithm and doesn't suffer from this problem of how we would do this. And then adding the preconditioned block CG, you get superlinear convergence with large enough block number. Which, whether this gives an actual gain depends on the cost of the linear algebra versus depends on the system and what's the memory bandwidth and stuff like that. But in principle, the block CG is actually helping here, and we've combined it with multigrid. Something I love about Hermitian systems, it's got a real spectrum. We can apply Chebyshev bandpass filters and produce ourselves a graphic equalizer. If you remember those, some of you will be too young, right? Remember these Iva and Sony hi-fis of the 1980s with these little bars that would dance up and down with a digital signal processor that would tell you the power spectrum in the audio range as live as the music went. But we have here a graphic equalizer for Krylov algorithms where we use order 5,000 expensive, I don't care, right? It's just a numerical experiment and one solve, right? So we can look as the thing converges at the final, actually in the final iteration, what is this power spectrum of different vectors that enter this multigrid, right? So we have here the coarse grid correction is 82% in the lowest eigenspan of matrix in this bin of our graphic equalizer. The smoother, so the residual is actually dominated by the highest bin, 87% in this bin, in the high end bin, etc. The smoother takes that power and corrects up the high bin and is left. The smoother is something like operative above 1 in the spectrum, said this lambda, the bandpass, the pass parameter is 1. The smoother moves the power in the residual out of this bin to the bin around 1, on either side, pins around that, on either side of 1 in terms of the power. So you can see that the action of the different matrices, and then Z is the Z is the overall precondition guy, and it has power both in the low portions and in around the smoother cutoff parameter there. So we kind of understand now and have a probe for how is this multigrid working spectrally versus the spectrum of the matrix. I think it's quite cute. Software performance, how am I doing for time? Yeah, 5 minutes. Okay, so we use tensor cores. We can get up to 100 teraflops per node in some of these systems. It's kind of crazy. The course, we profile this. I've said we'd use HIP, cycle CUDA, we've got portable code, etc. We've abstracted what's called batch gen. The nice thing about batch gen is I can take pointer lists, so I pre-allocate arrays with pre-allocated pointers for where the matrices are for the coarse grid operator and where the matrices are for its right-hand side, so that the hopping term in the right-hand side is actually encoded just by this pointer array, and I just go and say, hey, Mr. Machine Learning gem hardware, go and do this coarse grid operator for me, and it does it, right? Give me 10 teraflops per GPU. On Aurora, we profile things in detail. We've got communications here, so device-to-device copies intranodes running concurrently with calculation for the local portion of the operator. Then we collect the results that arrived and then add in the exterior portions, in a classic Halo Exchange PDE operator. This is all done with all sorts of fancy DMAs between GPUs and all that sort of stuff. going on just to sort of prove to you that we're really, even in a relatively small local volume, we've kind of Fabergé egg coded this and made sure that we're performing well. And it doesn't always work, right? An issue filed on GitHub saying incorrect results in the image on Aurora. Sorry, this is rare. It happens. They had a bug, and it was a rare bug because it was a bug that occurred because we were remembering device pointers you have previously used and they're mapping to memory. And if you free and reallocate that and get the same pointer back again, they were using that pointer incorrectly and remembering the old allocation and not the new allocation. Right, and giving wrong answers and in ways that were really pernicious, because if I changed one line of code to add an extra malloc, it would give the correct answer again.
Right? Did you ever find that?
Right. It was forensic to get it. I mean, I was check subbing packets coming in myself manually saying the CRC of this did not match the CRC of that, right? And they went, oops, yeah, now we understand it, right? So I can't complain too much. So we also have to work around the performance issue. We have a pipeline mode that doesn't work, and we are doing a pipeline from device memory to host memory, MPI only from host to host, not having MPI touch the device memory, and doing this all. Although I'm complaining, we're getting a significant portion of a significant resource. Yeah. Okay, Aurora scaling performance. So we scale well. The good news is after all this work, we can tolerate the issues and we scale well. On a log-log plot, everything looks kind of linear. On a more sensible plot where you look at the absolute performance, not a scaling plot that starts at 1 and goes up, because if you start really, really bad, you can always scale, right? So we start with measured teraflops versus per node versus number of nodes, and that is perfect scaling if it's flat and the eye can see a deviation. There is indeed a deviation, but it does not drop off too badly by any means. We scale well. Profiles of this is just conjugate gradient is kind of simple. It's just matrix application, linear combinations, dot product, repeat, calculate coefficient, repeat, right? The multigrid is somewhat more complicated, but we have polynomial smoother and a coarse grid correction. And if we zoom in on this, yeah, I'll skip over this. Basically, we have support for the matrix coarsening and for what I call a padded cell object that the halo exchange. The key point is that because we have this non-local 81 point stencil that fills in corners, we can fill in the corners with nearest neighbor exchange, as long as we exchange x in a dimension ordered sequence. We exchange in x and get the size here. If we then exchange what we've already exchanged in y, we get the corner terms of free with only local interactions, right? So you can build up this 81 point stencil without a complicated communication pattern that's reflective of that fill in. Then you feed it to the batch M hardware. We do this 81 point stencil as 9 batches of 9 terms and add them together. Yeah, I'm nearly done. Yeah. So in summary, right, our calculations, such as the prediction for mu on G-2, are critical to interpret the experiment. Big gain from multi-hands and multigrid, 20x faster than the original algorithm. Using tensor cores, GPUs for platform portable, and the level of work and detailed optimization is truly badly affecting productivity, right? It's distressing. Right.